All right, on Friday we talked about the idea of states of matter and fluids, and we have a solid, we have a liquid, we have a gas. We talk about a fluid is a material that will easily or that will flow. Okay, when you talk about a fluid, it will flow. So when you talk about fluids, you could be in a form of a liquid or you could be in the form of a gas, because both of them have fluids that will flow. We talked about the idea of density. Density is your mass divided by volume, and the thickness basically of a fluid or of anything, that is called a density. We talked about how we calculate volume, and when you're dealing with the volume of a liquid is, you can measure a volume in the liquid. There is no empty space in between. There's very little bit empty space between the molecules in this liquid here. When you talk about a gas and you talk about a volume of a gas, that is just the assumption, or that is the volume of the container that you have with respect to, how much gas you have in here. Well, there's just air that's in here, and we could say there's 24 fluid ounces of air, but we don't know what the actual molecules add up to. When you talk about the volume of a fluid, you can pretty much add up the volume of each individual molecule to be able to get the volume of a fluid. The volume of gas is basically empty space. When we talk about a liquid, liquids are not very compressible because there's not much space in between the molecules. We talk about a gas, there's a lot of space in between your air molecules that you have here. You can compress down. What happens when a mass is submerged in a fluid? If we take a mass and we submerge it in a fluid, if you have a tub full of water, if you have a tub full of water, you're taking a bath. Okay, you have a certain level of the tub and the water in the tub. If you sit down in that tub of water, the water level rises. If you fill the bathtub when you were little, you'd fill a bathtub up to, pretty tall, pretty high up before you go to take a bath. If you would get in the bath, sometimes the water would splash up over top of the bath, and parents wouldn't be very happy with you because there would be a puddle of water on the floor. Okay, so when you put water, when you have a fluid here and you submerge something in that fluid, the water level rises. It will go up. Well, Archimedes' principle is the volume of the displaced fluid is equivalent to the volume of the object fully immersed in the fluid, or that fraction of the volume below the surface level for a partially submerged liquid. Archimedes, he was born in 287 BC and died in 212 BC. So he 75 years old. Not bad for the BC era. You know he's the earlier ones because he only has a first name, only has one name, Archimedes. He's a Greek mathematician, born in Sicily and educated in Alexandria. Enjoyed fame in his lifetime for his many mathematical inventions, including the hydraulic screw, a device used to raise water from a lower to a higher level. Archimedes was also discovered the principle of a lever. After having found the mathematical laws which proved the principle true, Archimedes boasted, "Give me a place to stand and I will move the earth." He said he can move the earth if he has a place to stand with a lever. Archimedes considered mathematics as sort of sarcastic. So he had a sense of humor. Archimedes considered mathematics to be the only worthwhile science. There you go. Mathematics is the only worthwhile science. Circles fascinated him. He discovered the formulas for measuring different types of curved figures and worked out a method of approximating the value of pi. Archimedes considered his greatest discovery to be the formula for calculating the volume of a sphere. At his request, a sphere inscribed in a cylinder is engraved in his tomb. This guy had a screw loose, serving to remind the world of his proudest achievement. So Archimedes considers his greatest discovery the formula to calculate the volume of a sphere. At his request, a sphere inscribed in a cylinder is engraved on his tomb. I like this guy. He had a sense of humor to him. But if you have a volume placed in a fluid, the volume of the displaced fluid. Okay, so what is happening here is if we have a vat of fluid and we would submerge we'll do a circle since Archimedes liked the circles. If we would take this circle and move it down into the water. So we're taking the circle, we're moving it down into the water. This water level is going to rise to this new water level. So the water level is going to go up. Anytime that you submerge anything in a fluid, in a liquid, the water level rises. This volume of this displaced fluid, okay, this is the volume. The volume of this displaced fluid, which is this right here, whatever that volume is, okay, the volume is equivalent to the volume of the object immersed in the fluid. So to calculate this volume here is also the volume of the object. Or the fraction of the volume below the surface for an object that's only partially submerged. So if you only partially submerge this object, say you only take the circle and do it halfway, whatever is displaced here is the volume of the object that's below the surface of the water. So the volume of the displaced fluid is equal to the volume of object. So whatever the displaced fluid is also the volume of the object, which allows us to measure what our volume is. We can find what your volume of your body is by looking at maybe a dunk tank. If you want to think about a dunk tank, something that's a little bit smaller. You don't want to get too big, because if you go in the pool and you jump in the pool and go under the pool, under the surface of the pool, the water level's not going to rise that much, because it will go up a little bit, but to be able to calculate how much it actually gone up, that's tough to do, and then it's tough to calculate the volume of the water that's displaced. But as you jump in the pool, the water level rises. If you've ever been in a pool, and a lot of your friends, when you're little, a lot of your friends are also in that pool, water starts splashing over the top. Why? Because the water level rose from being this far from the top to about this far from the top, because there's a lot of bodies in there. So the volume really increases, or the volume of the bodies that are in there makes the water level rise. So whatever this volume that is displaced here, this volume right here that is displaced of this water is the volume of the object. Once again, we can put you in a dunk tank and submerge you in a dunk tank and see how much water, the water level rises, and calculate the volume of that water that's displaced. We can do the dimensions of the surface area. Most of the dunk tanks are squares. Okay, how much did the water level go up? And we can calculate the volume of the water that's displaced, and then calculate your volume. Apparent weight. Apparent weight is the weight of the object submerged in fluid. Your apparent weight is the weight of the object submerged in a fluid. Objects that are in a swimming pool that are heavy. If you're trying to pick up your friend and you're outside the pool, yes, you could probably pick up your friend, but it's tough to do. But if the person was on the bottom of the pool and you have to go down and save that person at the bottom of the pool, you could grab the person by the arm and pull them up top to the surface of the water. Why? Because objects in the water weigh less. They weigh less. That's your apparent weight. That is your apparent weight. When you talk about pressure, maybe, it's the magnitude of a force exerted on a surface. The magnitude of a force exerted on a surface. That is pressure. Pressure can be calculated by your force divided by your surface area. If we take a look at the units, this is a Newton per meter squared, maybe, which is also called a Pascal. We'll talk about Pascal's principle here eventually. So pressure is equal to force divided by area. Now, if you're in a swimming pool and you dive to the bottom of the deep end in the swimming pool, your ears start to hurt. Why do your ears start to hurt? Well, what you have is you have the pressure of the water that is pushing in on your eardrums. Okay, so you feel this force, your force of the water, pushing in on your eardrums. That creates pressure. You feel pressure on your head. You feel pressure on your face. You feel this pressure on your ears. It's pushing in. This force is pushing in on your head. Okay, pushing in on your head. Well, that's also pushing in when you get inside your ear. Is pushing in on your eardrums. So that force is pushing in on your eardrums, which creates pressure. That pressure is what's creating the pain for you. This is a vector quantity, Victor, because we have a force divided by a scalar. Looking at this, force is also equal to pressure times area. If we have pressure is equal to force divided by area, multiplying both sides by area, force is equal to pressure times area. When we get to the bottom of this pool, once again, what happens to your ears at the bottom of the pool? Ears start to hurt because of the pressure. The weight of the water is pushing in on your eardrums. The weight of the water, which causes that force, is pushing in on your eardrums. Which leads us to, what is called a buoyant force. The idea of a buoyant force. It's the net upward force exerted on an immersed object. Your net upward force exerted on an immersed object. So if we take a look at, we're going to put a cube in the water. Okay, so we're taking a look at this shape right here. We're going to say this is a cube. We have a cube there. And all these areas are going to be equal. So we have a cube with equal areas. Just going to keep it simple. We have a die. It's in the water. It's submerged in the water. Pressure is force divided by area. Force divided by area. Now, if we take a look at this force, the force that's being exerted on you is the weight of the water. This book has a weight to it. Okay, we have a weight here. If I would put it on my head, or if you would put it on your head, I feel the weight of this book on my head, which is causing pressure on my skull. Okay, so this force that you have, this weight of this book, is pushing down on the surface area of my dome. Okay, and that creates a pressure that is there. So the weight of this water that's on top of this cube is pushing down on it. Okay, so if we take a look at just this area right here, okay, just this area right here, this is the only thing that's above this square. So this weight that we have here is this right here. This is what is pushing down on the block. This weight over here is not pushing down on the block. This weight over here is not pushing down the block. The only thing that's pushing down the block is this force, this weight of this object or this water that's up above. Once again, when you go down to the bottom of a pool, that's the force that you feel on your body, on your head, on your ears. It's the weight of the water that's above you. Well, what we talked about on Friday was mass is the density of the water times volume. Because density is mass divided by volume. So the mass of this water, multiplying both sides by volume, is the density of the water times the volume of this water. So you have this volume that's up here that's above this cube. Once again, it's tough to do in two dimensionals, but if you want to think about this cube, you have this water that's on top of this cube that's pushing down. That water has a mass to it. When we talk about volume, the volume, what you have there is, thinking about this in 3Ds, the volume is basically a cylinder up above the water, or up above the cube. So if I had this submerged in water here, and I had this depth of water, I have this volume that's above it that is pushing down on top of it. And this volume is basically the area of this times whatever the height is. So whatever this area is here, that's pushing down and pushing down here, I can calculate an area of that top, and the height of this cylinder is the height or the depth of this water, H1. So doing some substitution, what we have here is we have, if I substitute in for this, my area times my height, I have the mass of the water is equal to the density of the water, the area of the top times my depth. So if I start substituting in for my mass of the water, I have density times my area times my height times gravity. So we're going to take this and substitute it in for the mass. Because the mass of the water is equal to density of the water, area of the top times the height 1. And I multiply that by gravity and divide by the area of the top. So if I take a look, my areas cancel out. So what we're left with is density of the water, height of the water, depth of the water times gravity. So no matter what the object is here, whatever this height is, this is going to be your pressure. Whether it's you, whether it's a dice, whether it's any type of object that is sitting there, this pressure can be calculated by density of the water, height of the water, times gravity. Well, if we take a look, that's my pressure on top. That's my pressure on top. My pressure on the bottom can be calculated the exact same way, but now we have height 2. So my force, or the pressure on the bottom, can be calculated by density of the water, height, times my gravity. Now, if we take a look at the cube submerged in water again, okay, I have this depth here and I have this depth here. My depth goes from here to here. So I have different pressures that are here. But if I look at the side here and the side here, they're both at the same height of the water. So my pressure here is going to be the same as the pressure over here. My pressure in front is going to be the same as my pressure in the back. What's going to be different is pressure on top and on the bottom. So my pressures on top, my pressure on top here, my pressure, this is my top, this is my bottom. The pressure on the bottom is going to be greater than the pressure on top. Why? Because H2 is greater than H1. H2 is greater than H1, which tells us pressure at 2 is going to be greater than the pressure at 1. Now, if we take a look, remembering force is equal to pressure times area, by what we talked about up here. Force is equal to pressure times area. If we look at the sum of the forces in the y direction, vertically, okay, because all the horizontal ones, once again, I'm pushing in from both sides, all those are going to be equal coming in from the side. So all those are going to net out to 0. But my pressure on top is going to be smaller than my pressure on the bottom. Or the pressure on the bottom is going to be greater than the pressure on top. So if I sum the forces in the y direction, this is my pressure. This is my pressure here. This is my area. Here's my pressure. Here's my area. So my pressure on the bottom here's my pressure on top. I can multiply by the area to make it a force. Okay, once again, all we're doing is we're going back to what we did back in chapter 2, and we started summing forces, or chapter 3 or chapter 4. We started summing the forces in different directions. So we're adding the forces in different directions. And how we calculate the force is, once again, pressure times area. Because force is equal to pressure times area. What we have common in both of these terms is I have density of the water, we have gravity, and we have area. That is common in both. So we can factor them out. So what we are left with here is density of the water, gravity times area, all times the quantity H2 minus H1. We're just factoring these values out. Now, if we take a look at one last step. If we take a look at the area of one of these faces, take the area of the bottom. Take the area of the bottom here and multiply that by H2 minus H1. Well, if I take a look, what is H2 minus H1? H2 minus H1 is this value right here. H2 is the depth of the bottom down to the bottom. H1 is the depth to the top. So H2 minus H1 is just the height of the object. So if we take the area of the base here and multiply by the height of the object, we just get the volume of the object. So if we look at this, this is equal just to the volume of the object. We're going to have a net upward force. You don't weigh as much in the water. Or if you're in the water, the tendency for you is to float. That's the buoyant force. The pushing up of you by the water. That's called the buoyant force. This net upward force is called the buoyant force, can be calculated by the density of the water, the gravity constant, times the volume of the object. Because this volume of the object can be calculated by this over here, which is a very unique idea to think about. The buoyancy, your buoyant force. Yes, we have the fluid here, which is the density of the fluid. But is also dependent on the volume of whatever object you have in there. Okay, which is, like I said, sort of a unique idea. Because you have the volume of this object, the volume of the object, the buoyant force is dependent on whatever the volume of that object is. Has nothing to do with respect to any volume that's being displaced or anything of that sort of the fluid. It depends on the density of the fluid. And if you think about the density of the fluid is equal to mass of the fluid divided by the volume of the fluid. That's where your volume comes in your mass of the fluid. Okay, density is equal to mass divided by volume. That's what affects any type of buoyant force. Oil is a lot more dense than water. If you jump into a swimming pool of water, you can swim to the bottom. Suppose that was filled with a bunch of motor oil, and you jumped into a pool of motor oil and tried to swim to the bottom. That would be difficult to do because you have such a thick fluid. The density of that fluid is much greater than the density of water. The density of oil is greater than the density of water, which means if the density of oil is greater than the density of the water, that means the buoyant force is going to be greater. If the buoyant force is going to be greater, the buoyant force is your net upward force. And it's tough to swim down through that net upward force. But if I have water, the density of water is not very dense. Okay, I can swim down through that depth. This here, once again, I'm going to add to your list of formulas. I'd also have pressure is equal to force divided by area. Make sure those are on there. We will pick up there tomorrow. We got other principles to deal with here. We got Bernoulli's, we got Pascal's, got a bunch of different other principles. All right, rest of the time's yours.